Yeah.
Okay, so we are very happy to have Daniel Neumann from IU to give a talk. He's as he just said, he started at IU about a year ago, and I think he would have liked to come to Purdue in person to give this talk if he has a car. But he will come. Next year March. So in the AMS sessions he will come. Hopefully at that time he already have a car and he can come in person to give a talk. But yeah, today this will be still via Zoom. So he will talk about Reshetikhin-Turaev invariants from twisted Drinfeld doubles and Reidemeister torsion. Go ahead, Daniel.
Right. So thank you very much for the invitation. I would like very much to be there, but still good to be virtually there. So I'll talk about certain invariants that we can get using something called topology and how they relate to well-known invariants like Reidemeister torsion. So I will begin by giving some motivation for this work and also stating the mean theorem. And then I will start with some definitions about braided categories and Taft algebras and stuff like that. And then I will move on in defining these things. So, yeah. So here's the motivation. So, well, everything is about invariance of knots and free manifolds. That is the object that we are interested in. So typically, we say that there are two classes of topological invariants. On one hand, there are the invariants that we can define using covering space theory, such as the Alexander polynomial, or more generally something called the twisted Alexander polynomials, which is something defined by Ian Wada in the 90s, which is something that depends on an additional structure of a representation of the fundamental group. And more generally, well, these invariants, they are particular cases of something called the Reidemeister torsion, which is defined for a CW complex and a representation raw of the fundamental group as here. Now, on the other hand, we have these so-called quantum invariants. So here, these are built using very different tools. I will briefly say how they are constructed using braided monoidal categories. So here, possibly the most famous of these invariants is the Jones polynomial of a knot. But there is a big family of these invariants, sometimes just referred as the Reshetikhin and Turaev invariants. Most of this theory comes from the work of Jones, Witten, and Reshetikhin and Turaev by the end of the 80s and the 90s. So once one has an invariant of a knot or a free manifold, one asks, well, what is the topological content of this invariant? So of course, by definition, an invariant is something that already has some topology on it because it's a topological invariant. But you would like that this invariant tells you more information about one knot. For instance, about the knot genus or four-dimensional properties like sliceness, or if your knot is an hyperbolic knot, you may ask whether this is related to the hyperbolic volume of the complement and stuff like that. So for this, there are two more famous knot invariants, the Alexander polynomial and the Jones polynomial. We can say the following. We can say, well, it's very well known that the Alexandrian polynomial gives you bounds to the knot genus. So that's why there is a ticket. It says something about knot genus. But the Jones polynomial, there is no such a thing for that invariant. If you ask about 4-dimensional stuff, then the Alexandrian polynomial also gives some information, at least in the topological setting. Namely, it gives some obstructions to not being topologically sliced, while there is nothing like that for the Jones polynomial, as far as I know, at least. And if you care about hyperbolic geometry, then as far as you know, there is no relation between the Alexandrian polynomial itself to the hyperbolic volume, but you can use these twisted Alexandrian polynomials, and then there are relations to hyperbolic volume. While on the other hand, for the Jones polynomial, these relations are still conjectural. So the motivation for this work is to sort of understand why this happened, why we have such properties for these invariants, but not similar properties for these invariants right here. So as a first step, and this is what is actually the content of the talk, we may ask, well, how is this invariant right here, Reidemeister torsion, an invariant, a quantum invariant? So here's the main theorem. Well, we will do that in the case of knots. So K will be a knot in the free sphere by xk, x sub whatever thing that always mean the complement of that thing in this talk. And rho will always mean a representation of the fundamental group into some other group. And for the moment, that will be SL and C. So here's the theorem. If we take the Reidemeister torsion of the complement of a knot relative to a non-modulus in the boundary, so here M is a meridian in the boundary, then this invariant, it can be obtained using this Reshetikhin-Turaev construction of quantum invariants, but you need to find the appropriate object to apply this construction, and that object is it is a graded category graded by this group, and that category is something that maybe the fancy term is that it's a relative Dreamface center of a cross product category. So that is the object. I won't talk too much about that. I will talk later about some sort of simpler version of this object, which is something called a twisted Drinfeld double of a Hopf algebra. And in this case, that Hopf algebra is just an exterior algebra over this vector space. So, well, this is actually a simplified version of the theorem that is easy to state. Sort of the more general theorem is that actually, first, here you may not only consider this Hopf algebra right here, but you could put any Hopf algebra H of finite dimension maybe, and you can consider a similar object and get kind of similar invariants. And when H is involutory, then this invariant recovers an invariant that I defined in my PhD thesis, which is some sort of Fox calculus twisted version of another quantum invariant called the Kuperberg invariant. But yeah, I'm not going to talk too much about that. I will maybe talk about this side of the story. So the goal of the idea here is that we get a family of invariants out of graded categories, And these invariants, they still have some Fox calculus on it. So that means they are quantum invariants, but they still capture a little bit about covering spaces. So hopefully this construction is something that is going to have properties like the ones right here. But we are not yet there. So let's begin with some well, definitions of all the stuff I've been talking about. So here we are interested in monoidal categories. By that we mean a category with a tensor product and a unit object, and well, with a bunch of axioms that I'm not going to state, but here is the main example. If you take a Hopf algebra over a field, and you take the category of modules over that Hopf algebra, then that is a monoidal category. So what do I mean by a Hopf algebra? So here I recall this definition. So by that we mean, well, first it's an algebra over a field, then it has some additional structure, namely a co-multiplication that is a map from H into H tensor H, and a co-unit from H into K. These two maps, they have to be algebra morphisms. And there is an additional piece of structure called the antipode that goes from H to H, and there is a bunch of relations. So representation categories of Hopf algebras, they are monoidal categories because, well, if H acts on a module U, and if H acts on a module V, then the tensor product of these two things, that is a module over H tensor H, but using this co-multiplication, you can bring it back to a module over H. So you can take tensor product of modules, so you get a monoidal category. Right, so I will need to introduce some notations for Hopf algebras. So I will use this so-called tensor network notation, where the multiplication, which is a map from H tensor H into H, that is denoted by well, a diagram like this with two inputs and one output, where the top one corresponds to the first factor of H and the bottom one corresponds to the second one, like that. So similarly for the co-multiplication and the antipode. So for instance, to say that this thing is a morphism of algebras means that you have something like that. That is something like that. Then the arrows cross each other, and then you have a multiplication right here. So here are a couple examples of algebras. First, of course, finite groups gives you examples. You just define the co-multiplication in this way, epsilon of, well, here G is an element of the group. And the antipode is just inversion. Here is the example we are interested in this talk, which is just an exterior algebra over a finite dimensional vector space. So that is, again, a Hopf algebra if you define the co-multiplication in this way for every vector in the vector space, and then, well, epsilon and s in this way. So these two examples are sort of very, maybe very trivial. And here is a more interesting example, which is what is usually called a Taft algebra, where you take two generators, one that is invertible, and they don't commute to each other, but they co-commute to each other. And that can also be given a Hopf algebra structure in this way. So we will say that a monoidal category, so with tensor and unit that is braided, if in some sense it is commutative. So X tensor Y is isomorphic to Y tensor X, but more precisely, we have a collection of natural isomorphisms during this commutation. And we need to require a couple relations for these natural isomorphisms. So the idea of considering these braided categories is that from this relation, if you set X equals to Y equals to Z, then you can see that this thing right here satisfies the usual Yang-Baxter equation. And so that gives you immediately a representation of the braid groups into endomorphisms of this object X that you took in your category. Right. So this, we have a representation of the braid groups, and with a little bit more work, with a little bit more conditions on our category, we can actually extend this construction to tangles in R squared times an interval. Where to say that a category is ribbon means that it has duals, so we can take the dual of an object in the category, and there is also a collection of twists, which are isomorphisms from an object to itself, and there is a bunch of actions that sort of make this theorem work. Right. So far, everything sounds a little bit abstract. I will go in. I will specialize to Hopf algebras very soon. But the reason of going into braided categories is that they give also some sort of natural way to give very many examples of these things, even if we are interested just in Hopf algebras. So let's start with this idea. So let's suppose that M is just a monoid, which is sort of the set theoretic version of a monoid category. So just a set with an operation. Then we know very well we can take the center of this monoid, just the elements that commute to all the elements of M, and that is a commutative point. Very simple. So we will try to categorify this thing. So do the same thing, but with categories. And that leads to something called the Dreamface center of a category. So here, given a monoidal category, so C, tensor, and a unit, we can define a new category, which is the category what? It's an object of the previous category, but together with a family of isomorphisms from X tensor Y into Y tensor X. So in some sense, this is like the center of the monoid as before, but we cannot take equality because we are in a category, so we need to fix a family of isomorphisms. This is replacing the equality that we had before. And of course, we need to require a couple of things about that. And one can show that this new category is always braided. So we are sort of very close to get link invariance out of this. So this is very abstract, but this is what I want to talk about. When C is the category of modulus of a Hopf algebra, then this Dreamface center is it can be shown that this is also the category of modulus over a new Hopf algebra, and that new Hopf algebra is, as a vector space, it's H dual tensor H. But the algebra structure of this thing, it's a little bit more complicated. So here I'm using this tensor network notation I introduced before. But here an arrow oriented to the left, that means an element of the dual Hopf algebra. So P in H star, and here we have an element in H. So this is telling you that P tensor A Q tensor B, where P and Q are functionals and A and B are elements in the Hopf algebra. How do you compute that product? Well, first you take this triple co-multiplication of this element right here, a triple co-multiplication of this element right here, and then you pair these guys together and multiply sort of what remains. So it's a strange looking formula, but this sort of this is really this Dreamface center construction that I was talking about. Right. So this is what we call the Drinfeld double of a Hopf algebra, and the braiding in the category of models of that thing, we can understand this very easily. That is essentially left multiplication by an element in DH tensor DH, and which is that element where you take a basis of H and you take epsilon tensor HI, that is an element of the H, and here you take the dual basis tensor, the unit of the Hopf algebra. So I will just denote this as H lower I tensor H upper I, and this first HI is an element of the Hopf algebra, a thought as an element of the Drinfeld double, and this H upper I is an element of the dual Hopf algebra. So this story so far leads to invariants like the Jones polynomial or the Humphrey polynomial. But we said at the beginning that we want to get invariants, for instance, Reidemeister torsion. So how do we get such a thing if this depends on this additional structure, namely a representation of the fundamental group? Well, there is an extension of this theory due to Turaev from the 2000s, in which instead of a braided category, you take now sort of an equivariant version of that notion, so a G-braided category, and what you get is a family of invariants of tangles in R2 times an interval together with a representation of the fundamental group into G. So to say that a category is G-braided means a couple of things. Where we say it's at this joint union of categories, one category for each element of the group, and the tensor product satisfy this condition right here. But we also require that the group G acts over the category by monoidal functors, again satisfying some relations, and then the braiding, it's sort of a little bit different than before. Here the braiding, we want the this X right here, we want it to be, oh, I'm sorry, that was supposed to be Y, and this was supposed to be X, where X belongs to C alpha. Sorry for that mistake.
Oh, Daniel, so I just want to make a comment.
Yeah, sure.
So nowadays, I mean, this category now is called mostly, and most people call it G-crossed braided categories.
Yeah, that is right.
Yeah.
Sorry, oh yeah, I was here. Yeah, that's right. Yeah, this is that's sort of the best word for it. It's a G-crossed braided category.
Yeah.
I just said G-braided for simplicity.
Sure.
But yeah, it's a G-crossed category, where the crossing is this family of monoidal functors on the category. So the group action G on the category. So I will focus on a special case of this construction, which is called a twisted Drinfeld double. So it's very much like the thing that we had before, but yeah, these strands will be twisted by automorphisms of a Hopf algebra. So here's the idea. We can take any finite dimensional Hopf algebra, With a mild condition, I will sort of suppose that the Drinfeld double of this is already ribbon. That is not always true, but if it's not true, you can sort of extend H so that it is true. It is just a very mild condition. So in particular, the antipode of the Drinfeld double squares to conjugation by some element in this the Drinfeld double. And yeah, right. So here's the thing. In what follows, my group G will be the group of Hopf-algebra automorphisms of H. And for each automorphism of H, I will define a new algebra, which as a vector space is the same thing as before. But I will put this alpha somewhere in the middle, namely here when we had an element of A and here a Q in H star, where when we apply this triple commultiplication and this triple commultiplication in the dual, instead of pairing them just with the antipode, I will further twist with the inverse of this automorphism. Now, if we do that, this thing is no longer going to be a Hopf-algebra, unless alpha is the identity where we just recover the previous Drinfeld double. But there is still a commultiplication that sort of respects the group structure. So what does it mean? It means that essentially we have found a G cross category as before. So if we take the category of modulus of that thing, then that is going to be a G cross category as I mentioned before. And for the experts, I will just say that here is maybe a more usual name to this category. It's actually a relative Drinfeld center of a cross product category. Anyway, I would like to be a little bit more explicit about the action and the braiding in this category. So, rather, I will sort of forget about the structure of the category and work just over the Hopf-algebra itself. So this G action in the category comes from a family of algebraic isomorphisms. So from D beta into D beta conjugated by alpha, where alpha is the label of my isomorphism. And this guy is defining this way, just sort of composition with this automorphism. Now, on the other hand, my the braiding of this category, it will be very similar to the one that we had before. Sorry, that was a few pages before. So we take a basis of H and the dual basis. We take HI tensor HI, but we twist one side by the one of these automorphisms.
Sorry.
Yeah.
Can I ask this definition of phi alpha? So D alpha. Actually, this phi alpha. This is action on the algebra or on the category. Yeah.
So yeah, I will. Yeah, soon I will just be working with Hopf-algebras, so that's why I'm doing everything with Hopf-algebras. But
oh,
so, yeah, okay. This is an algebraic isomorphism between these algebras.
Okay.
But then
that induces a
exactly that gives you this action from this way just by composition with the inverse of that thing.
Okay.
I also have a question.
Yeah, sure.
When you define the twisted double, that's not a Hopf-algebra. Can you describe the failure of not being a Hopf-algebra in terms of the twisting explicitly?
Oh, yeah, great question. So Good question. So actually, yeah, I'm sorry. I should maybe not say that it's not a Hopf algebra, but rather it's not naturally a Hopf algebra.
Mhm.
So here, yeah, I mean, I don't know if for alpha different from the identity, this thing can be given some algebra structure, but it's not a Hopf algebra in a natural way. So if you take the usual commultiplication for the Drinfeld double, this is not going to be a commultiplication for that thing because of the twist. But what you can do is,
When you say it's not going to be a co-multiplication, you mean it's not going to be compatible with the product?
yeah, exactly. It's not an algebra morphism.
Mhm.
So the only algebra morphism, so the only natural algebra morphism that you can get goes this way. And this thing is also twisted. It's co-multiplication of a beta of p tensor h, that is p2 tensor h1 tensor p1 tensor twist of the h2, something like that.
I see. So with this coproduct is a Hopf algebra.
No, it's all sort of so I mean, for one alpha, this is not a Hopf algebra. You sort of need to take that coproduct I just wrote is just an algebra morphism from d alpha beta into d alpha tensor d beta.
Oh, I see. I see. They're different. Okay, good.
Yeah.
Yeah.
So yeah, it's.
But this is what you use this to define the representation category, right?
Right. So
I see.
this multiplication. So the fact that this multiplication goes this way is what implies that is implying this condition right here.
Mm-hmm. I see.
Okay, just if there are more questions, just stop me. So how do we build invariants of tangles with this stuff? So I will mainly consider one tangles in this talk, and well, I will restrict to this twisted Drinfeld double thing. So I will take a representation from P1 into the group of Hopf algebra automorphisms. And here is the idea. Well, first we draw a diagram of our tangle. And what we are going to do is to label the edges with elements of the group. So how do we do that? Very simple. We take a base point that we think that it's outside the page, and then we draw a loop that encircles each edge with well, linking number -1 in this case. And then for each one of these loops, we apply rho to that, and we get an automorphism in the Hopf algebra, which is our group G. So I will put these elements as labels of the edge. So here's alpha, which is rho of this thing right here, similarly for beta. And then, of course, whenever you have a crossing, then this thing right here, it is conjugation by alpha. Okay, so here is the idea. How are we going to get invariance of these things? Well, of course, I'm assuming that I already choose on this twisted Drinfeld double of a Hopf algebra. And so we have these elements R alpha beta that were just the dual sort of a basis of H together with the dual basis, but twisted by some automorphism. So what we are going to do is at each crossing, we will put one, well, we will just put one. So the first entry in this tensor product on the overstrand and the second one on the understrand. And I will put a label with an automorphism just after this element in the dual Hopf algebra here. Well, there is a tiny little additional step, namely, whenever we have right caps and caps, like these guys right here, then we need to put this group like of the Drinfeld double. And but whenever there is a left cap, we just do nothing. Yeah, so everything is clear with an example. So let's say we have a 1-1 tangle with closure the right 3-point knot. So in this case, for each one of these crossings, we need to apply the rule that we had before. So for each crossing, we put an error matrix, but now this error matrix, it is twisted by an automorphism, like here. So here the label is alpha, so we put alpha of hi, and here is the dual. Here in this case, the label is the conjugation of this label by alpha. So we need to apply that, and so on. And the idea is the following. Starting from the bottom of this tangle, we will follow the orientation and multiply all the elements together as we encounter them. But each time we see these white dots, which are labeled by this phi alpha, which is, I recall you, that is an isomorphism from d alpha to, from d beta to d alpha beta alpha minus 1. Then we need to evaluate the whole thing on that phi alpha. So here's an example. In this case, if we start here gathering all these elements, so we will actually multiply from right to left. So we start with this alpha of hi, we multiply by hj dual. Then we evaluate this product on this the automorphism corresponding to this crossing. So that is phi of alpha beta alpha minus 1, and so forth. Then we multiply with this. Here there is a group like G, and so on. So it's a big product that looks a little bit ugly, but well, at the end of the day, we get an element which I will denote by Z rho h of t. So it depends on the tangle, on a Hopf algebra, and on a representation of P1 of the complement into the group of automorphisms. So essentially from this theory of Reshetikhin and Turaev, it follows that this thing is an invariant of this pair right here. So the tangle together with this representation. And well, eventually I would like to get invariance of knots, and this is going not necessarily to be an invariant of the closure of the tangle, but yeah. So the idea here is that if we have two 1-1 tangles that have the same closure, but the closure as a G knot, so it's a knot together with this representation, then what we can say is that these two guys, they are almost isotropic, but that is just up to conjugation of one of these representations. So if we want to get an invariant of the closure, so a knot together with the representation of Q1, we need to evaluate on something that is invariant under these phi alphas. And I will do something very, very simple. I will evaluate over the counit of the Drinfeld double. So that usually, if you do that for the untwisted invariant, so without this row right here, that will just be 1. So a very trivial thing. But in this case, in the twisted case, you get something that is kind of not trivial. So for instance, if your Hopf algebra was an extended algebra over this, over a three-dimensional vector space, then this thing right here, so epsilon of this invariant right here is actually going to be the Reidemeister torsion of the complement relative to a meridian. So I think that the best way to see this is with an example. And I need some, this. Right. So I wanted to do this computation for the trefoil so that you could see how sort of Fox calculus appears. And in particular, for this Hopf algebra, we recover Reidemeister torsion. So here, I guess I should copy this thing right here. Can I do that? Oh, that's great. So how does this computation actually look like? So I will do the following. So first, recall that these are alpha betas. They are just, they have this form where this is an element, well, that is a basis in H, and this is a basis in H dual. So this thing, we will denote it in this way. So recall that we have this tensor network notation, but I will change things a little bit. And now elements in the dual will be arrows going down, and elements in H will be arrows going up. And to say that these are dual to each other means that we can write this in this way. So as a cup. But then there is an alpha that is twisting one side. So here we have three air matrices. That means that we have something like this. And I guess I will be using too much space. Oh, that is the one to use. So here we get an beta, then that will be let's call this gamma actually. So gamma will be this guy right here, and this is going to be alpha. Yeah, and I will also change a little bit the conventions. I will actually start from the top and multiply the guys in that order. So that means I will first start, so that was the K, J, and the A. I will start with this guy here, and then I need to multiply with this guy right here, which is this one there. But if you multiply an element of H star on the left and then by an element of H, that is just stacking those two guys together. So we just stack these two strands together and we do nothing else. But then, well, if we keep following, we encounter one of these automorphisms. In this case, a phi alpha. And since we are going the other way around, we need to evaluate the whole thing on phi alpha minus 1. So that means alpha here and alpha minus 1 there. And then we encounter this guy right here. And here's where things become a little bit ugly. Am I right? Yeah. So we get an inverse antipode. Then, oh yeah. So, yeah, I'm sorry. So here we have to think that if this strand is labeled by beta, then each element here belongs to D of beta. So the product that we are going to use now is the product of that thing. So that means beta minus 1. And we get something like that, as in our previous pictures. And then this, well, these guys, they are multiplied together. And then, well, there is a group like in here, but just for simplicity, I will suppose that my group like is just the unit of the Drinfeld double. So now if I am where I am right here, and I go there, then I have this beta of 8k. So I have this guy here that gets multiplied, and then the whole thing passes through this E of gamma. So that means gamma and gamma minus 1. And then finally, we multiply by j, which is this guy right here. And again, things become a little bit messy. There is another of these products right here, is minus 1, and everything happens in alpha. So that means this product right here. So you see that it's a little bit difficult to write. So it is not very clear what we are going to get. Right, and then these two guys are multiplied together. And this, oh, what I did here, so I confused myself. This is multiplied by this one. So that means there. So there is a little mistake in here, and that's very unfortunate. Oh yeah, yeah, I'm sorry. Yeah, that was this thing right here. I made it wrong from the beginning. That is supposed to be going down, and then this guy goes up. So, well, as you see, we have no idea what this thing is, and these Drinfeld double multiplications look very messy. But we said before that we are going to evaluate on the co-unit of that thing. So that means we apply epsilon and 1, and that is going to simplify a little bit the picture. But actually, I want to do something else before we simplify this picture. Yeah, and I see that I just have 10 minutes. So I don't know if I'm going to be able to do the whole computation. So yeah, I wanted to do the whole computation, but I'm running out of time, so I will miss a couple of steps. So at the very end, well, if we apply this epsilon, that means a huge chunk of this huge tensor is going to disappear. Actually, a lot is going to disappear. But if we do that, it's not going to be very clear what we are going to get. So at the end, what I wanted to get was the following tensor, something like this, that looks like this. And here there is gamma minus 1, S minus 1, alpha minus 1. There is a gamma right here. And yeah, that goes there. And this one goes up and down. So yeah, that is what we should get at the very end. So now this is not yet very clear what that is. But then, well, here we are applying a couple of traces in here. So that means the trace of something. And I will use a formula of Rutherford for the trace. So that is well, it's a formula that expresses the trace something like this in the following way. And maybe I hope not to get this wrong. So I guess there is some there is an antipode in here, and then these two guys, they swap, and there is a multiplication, a co-multiplication in here. But then we need to evaluate on something called the Taft algebra integral and the Taft algebra co-integral. So what we get then is something that looks like this. Well, I will need to swap in here, but that is not going to be very important because we want to specialize to a commutative Hopf algebra. Integrals, this becomes a multiplication with co-integrals. And then there are some additional antipodes in this here. Actually, it may be an inverse antipode depending on whether these are left or right integrals. So what is this? Oh, yeah, that was supposed to be my final computation slide. So I need to do something like this. So far, not clear what this thing is, but let's specialize to the case of our exterior algebra. Well, then in that case, sort of combining these integrals and co-integrals amounts to sort of taking the determinant of something. And this tensor right here in the middle, that is essentially a matrix. So this is the determinant of a matrix. And how do we read that matrix? Well, what we do is, well, first, here there is an alpha minus 1. So that means, so let's say this is 1 and 2. So there will be an alpha minus 1 here because this is going right there. But here, that is an inverse antipode, which is going to be minus 1. That is just because S of B is minus B in this Hopf algebra. But now this other guy right here, you see a gamma minus 1, alpha minus 1 gamma going there, the first one. So that means, and there is also an inverse antipode. So you get, well, that was minus gamma alpha minus 1 gamma minus 1. And this one right here becomes just 1. And this guy right here going to the second factor, that is minus 1. And what is that thing? Well, that is just the determinant of, well, there is a little sigma right here, but anyways, this is the Fox calculus computation for Reidemeister torsion. So here you take these relators relative to these generators, where these relators, they come from this Wirtgen representation. So for instance, this R2, that is going to be, I hope to get the right one. I guess that is gamma. No, that is, sorry, that is R1. I switch a little bit my conventions. So then if you take the derivative T R1 to T gamma, then what you get is 1 minus gamma alpha gamma minus 1. And then if you apply this sigma, which is, well, inversion on this group ring, then you get exactly these terms right here. Well, so we get Fox calculus, and sort of Fox calculus comes from, well, from the twist in this twisted Drinfeld double, and also from these automorphisms that we plot at the crossings. So here, of course, this is the example of an extended algebra, but sort of, you can think that for an arbitrary Hopf algebra, this is some sort of Fox calculus twisted version of the universal Reshetikhin and Turaev invariant at a Drinfeld double. And just to finish, well, so far we've been talking about invariants which are numerical invariants, But yeah, so sorry, just a question. Do I have to finish at 12:30 or a few minutes before that?
I guess it's fine. It's pretty flexible. So
Okay. Well, so just very short. When our Hopf algebras are graded by the integers, then there is the following trick that we may do. Where previously we had automorphisms going from P1 into the group of Hopf algebra automorphisms. But if we extend this Hopf algebra with a polynomial ring, then we can also extend this automorphism to that thing. Well, in this way, we just sort of keep track of this delta of the homology class of this delta right here that is appearing right here multiplied by the degree in the Hopf algebra. So why do we do this? Because now our previous invariant, which was just a number, now becomes a polynomial. And in this case, the theorem will be that, well, in the case of an integral algebra, that this thing right here, this torsion twisted by, well, the same representation, but that thing is essentially the twisted Alexander polynomial of a knot twisted by that representation. So sort of, this is sort of giving you a way to define some sort of topological twisted Alexander polynomial. Yeah, which still don't know very well what that is in general, but I think I can finish right there. So thank you very much.
yeah, thanks a lot, Daniel, for this next talk. Yeah, I have a number of questions, but I want to first ask if other people have any comments or questions.
I was wondering if you have kind of analyzed this to or specialized this to Hopf algebras which arise from, let's say, quantum groups.
Yeah.
Like maybe a simple example like quantum SL2C or something. Do you get anything
yeah,
known?
that is a great question. And honestly, I still don't know very well. Well, actually, I don't know at all. It's like, so here, well, I was taking this Drinfeld double, but you may think, yeah, yeah, actually, that's why I had this example at the beginning of just a Taft algebra where you just have this single Q commutation relation.
Right.
So if this is your Hopf algebra, well, maybe not exactly that thing, but I don't know, with a Q square and something like that.
Right.
If you take the Drinfeld double of that, then you get something that quotients to UQSL2. So you still get, I don't know, Jones polynomials and stuff like that from Drinfeld doubles of that thing. But now this invariant that we get, where this uses this twisted Drinfeld double, and if your representation was just the trivial one, then that would be just the previous invariant, right? So sort of, this is saying that there is a twisted version of the usual quantum invariance that you can get from quantum SL2. Sort of, well, in that case, moreover, your Hopf algebra is graded, so you can do this trick of introducing an additional variable coming from the grading of the Hopf algebra. So yeah, it looks like there is some sort of two variable not invariant hiding behind there, but I really don't know what that thing is. I thought that could be the Humphrey polynomial, but the Humphrey polynomial comes more like from SLN, so the Lie algebra SLN. So it's not really like this thing. It's sort of another thing that I don't understand very well. And yeah, so in short, I don't know. sorry for that.
Yeah.
Any other questions? Okay, so maybe it's my turn. In for the invariant, you defined like you define from this twisted quantum double. Is this originally given by Turaev and Reshetikhin?
Sorry for this, for the twisted.
Yeah, for the twisted.
Oh yeah, because I said Reshetikhin and Turaev. No, this yeah, I mean, it is essentially the Reshetikhin-Turaev construction, or it's essentially that construction and that proof. But yeah, this is, I should say, Reshetikhin-Turaev and Turaev. So this sort of follows from this paper, this homotopy quantum field theory paper, anti-cross categories, stuff like that.
Yeah, because I mean, I was asking this because this is, I mean, this is like similar to the Hanning's invariant. I'm not sure if you're familiar with that.
Right.
Like if you take basically the trivial group, then this construction of the invariant is basically like the Hanning's invariant. Yeah, I mean, so I mean, this is kind of like historical.
Right. In the case of closed-field manifolds.
Yeah. Also, yeah, that comes to my second question. If this invariant, can this invariant be extended to 3 manifolds?
Yeah, great question. Yeah, well, in short, I don't know. I haven't worked out a couple extensions yet. For instance, I'm talking about knots, not even about links, because I'm using this sort of that 1-1 tangles are essentially knots, which is not true for links. And so I mean, yeah, I will just say, yeah, these things should extend to closed-field manifolds using some great version of the Henning construction. But yeah, but there is, I mean, it's not going to be totally straightforward, or maybe it is, because sort of, well, I don't know. I have to say I don't know, but I mean, what would you like to get if you extend this to closed-field manifolds? You would like to get the Reidemeister torsion of a closed-field manifolds in the case of an exterior algebra, right? But when you talk about closed-field manifolds, it's a little bit more complicated to talk about Reidemeister torsion because you need these representations to be acyclic. In this case, we didn't really care about acyclicity, but that was because I took this. Oh, am I still sharing my screen? Or?
Yeah.
Oh, yeah, I cannot see that. Sorry. Oh, yeah. In this, we sort of took this relative torsion so that we didn't have to care about acyclicity. But if you want to talk about just a closed-field manifold, you will need to take care about that. And I don't know really well how is that going to, yeah, how is that going to appear in the Henning construction? It should be something general about Taft Algebra. So I don't know. Maybe it's something about this modified traces and stuff like that. But yeah, there is something in there that.
Okay.
Really
Is there also a Kuiperberg version of this invariant?
Yeah. So yeah, as I said in the beginning, sort of very short. What I had worked in my thesis was sort of the Kuiperberg version of this construction, where yeah, and it was in the Kuiperberg version. Since in the Kuiperberg version you just take care of the Taft algebras and not of the Drinfeld doubles. It was very easy to see how Fox calculus appears from Taft algebras, and in particular, how Reidemeister torsion was a special case of a twisted Kuiperberg invariant. So sort of this theorem right here is sort of the Drinfeld double version of that thing.
Yeah.
But the idea of doing this is that now our Hopf algebras don't need to be involutory as I had done in my thesis. And,
Sure. Yeah. Mhm. Yeah, I mean, this is sort of the relation, like an analogy of the relation between the original Kubrick invariant and the Henning's invariant. Basically, the
Right.
Henning's invariant from the Drinfeld double is equal to the Kubrick invariant from a Hopf algebra. So it seems like, what you are doing, and also in your thesis, is like a G-traced version of that.
Exactly, that is exactly. So what I did in my thesis is sort of, it is secretly, so what Kuperberg invariants are defined using Hopf algebras, right? And in that case, it was some sort of, not really a Hopf algebra, it was a graded Hopf algebra associated to that. But sort of the category of modules of that graded thing is that thing in the middle. It's a category of modules cross product with the group of Hopf algebra automorphisms. Yeah, so that was sort of this sacred object I was considering, and sort of using what you're saying, and also there is also this work of Turaev and Viollet that say that Reshetikhin and Turaev at a relative Dreamface center is the Turaev zero of the previous category. Then sort of the natural thing to do was to consider this relative Dreamface center.
Sure. Okay, got it. All right. Are there any other questions for Daniel? All right. Okay, then thanks again, Daniel, a lot for this talk. Hope to see you sometime in person later in the future.
Sure. Hopefully in March.
Yeah. Okay. Yeah. If there's no other questions, then I guess yeah, I'll see you in March, if not earlier.
Thank you.
Yeah.
Hey, thank you for the invitation, and see you in March. Hopefully before that, but I don't know. At least March.
Yeah, no problem. Yeah.
Okay.
Bye.
See you guys.
See you.